Hello and welcome to this lecture. We are going to talk about a couple of things in this lecture. The first thing is fixed point implementation for the decoder. I think I mentioned it briefly before. I want to say a few more things systematically about it. And the second thing we will see is rate matching for the LDPC code and the 5G standard. So, how that is done is like I said, precisely described in the standard, but I will point out a simple implementation for the rate matching that I will do. Okay, so it can be modified later on. These are the two things we will do in this lecture. So let's get started. So, if you remember the basic model that we have BPSK, which takes 0 to plus 1, 1 to minus 1. And then we have the received value after additive white Gaussian noise. R is S plus some noise, right. So, now this is plus 1 or minus 1, and this is Gaussian random variable, mean 0, and variance is going to be some sigma square that you will pick in the simulation based on the EB over N naught that you want. Okay, so this is the picture. So, if you want to draw it on an axis, you can draw the value of R on an axis. You have plus 1 here, minus 1 here, okay, and the values are going to be around this minus 1, maybe depends on the sigma square, right. So, you can have all sorts of values. This is what you have. Okay. So, generally as per this model, this R is a real value. So, what do I mean by a real value? You could get something like 1.002345, things like that. So, the precision can be very high or something like that. At least in the model, the way we write MATLAB code, MATLAB uses double precision numbers. So, they have quite a few decimal points. Okay. So, maybe 32 bits, 64 bits, like that. Okay. So, however, in implementations, when you want to put your decoder on a chip or on a processor on a board which has low power, typically people don't use such very high levels of quantization. So, you can't use 64 bits per received value, and all that is really hard. In fact, the number of bits they will allow is depending on the area that you can have on the chip, etc., maybe just 5 bits or 4 bits per value. So, this is theoretically infinite precision. In theory, so in practice, double precision, say in most commuting in software, when you do simulations, you're probably using 32 bits, 64 bits these days. Okay, so that's what is double precision. So in hardware, you probably want 5 bits per received value. Okay, so you have to quantize. And I'll mention briefly how I'm going to do the quantizing. This is how it's done typically. Okay. So, when you quantize, usually first thing you do is set a maximum possible value. So, you will clip your the value that you consider to some region. So, for instance, R equals S plus N, N is Gaussian. Gaussian can be plus infinity, minus infinity. It can take a very large value. Sometimes, occasionally, it does happen. Okay. So, in practice, what you do is first you clip it to some R max. Okay, R max minus R max. Okay. So, what I will do is R will come in and I will clip, and I will get some R prime which is clipped. So, what will this do? So, R prime equals R if R is between minus plus R max and minus R max. And this will be, I should put something like this, it will be minus R max if R is lesser than minus R max, and it will be plus R max if R is greater than R max. So, this is the clipping operation. So, if you go above R max or below minus R max, you set it as R max. Okay. So, a typical value for R max could be could be 3 or 4 or something like that. In this case, for the BPSK case, that seems fine enough. You don't need much more than that. So notice I'm doing 3 or 4. I'm assuming the received symbol is +1 or -1 plus noise. So there'll be some gains in your receiver chain to make sure that that happens correctly. Okay. So R max and minus R max is typically for the decoding purpose. You could take it as 3 or 4. It's not wrong. Okay. So once you decide on an R max, the values in between have to be represented by just 5 bits. Okay. So now let's say we'll take 6 bits just for having some convenience. So if you look at 6 bits, 1 bit is going to show you sign, right? So 1 bit. So then after this, R prime has to be quantized to say 6 bits. Okay, 1 bit is sign. The remaining 5 bits is magnitude. Okay, so that's one way to think about it. So you can do a very quick and dirty operation to do this quantization. It's pretty good in most cases. So you take the maximum integer that you want to allow. It's just 31, right? So if you have 5 bits, you can go from -31 to 31. Okay, so those of you who know the 2's complement method of representation will tell me it's -32 to +31, but we'll just keep it as 31. Okay, so we'll take -31 to +31 as the maximum integer, and you have R max and you have this R prime as well. And what I will do is, for quantizing, is simply first divide by R max. Okay, and then I will multiply this with max int, and then take the integer part of it. Okay, so this is a very convenient and simple way to do quantization. So this is the quantized value. Okay, so hopefully this is clear to you. Okay, so you take R prime, the clipped value, divide by R max, multiply by max int, and take the integer value. You could take floor or seal or something like that. It doesn't matter. So you can take the integer value. Okay, so this gives you integers. So what will happen once you do this is, in the receiver you will have integer value. So you can see automatically 1 bit becomes sign, 5 bit becomes magnitude when you do this. If R prime is negative, this integer is going to be negative. So it will be -5 or +5 or things like that. So I'll show you when we write this in MATLAB how the values look. But this is how it works. So you have your received value, you clip it, then you quantize, you get integer values. So these are integers from -31 to +31. Okay, and you work with this integer in your decoder. Okay, so you may be doing operations with this integer. You may add them. If you add, you have to make sure that you don't exceed too large a number. So all that you have to take care of. Okay. So I'll stop with this as far as this course is concerned. So we will do quantization and we'll work with quantized values. So now quantization has some effect on the decoders. These decoders we implement are suboptimal. So you have to be slightly careful when you quantize and watch out for things that happen because of quantization. Okay. So one of the effects is quantization makes received values equal. Okay. So for instance, you may never get 2 received values which are the same if you don't quantize, but if you quantize, you will get the same values. So because of that, there can be some suboptimality. Of course, there will be suboptimality, and you have to take care of those things when you in the decoder. Okay, so some things to watch out for, but generally this will work. What works with real values will typically work with these kind of integer values as well. Okay, so this is how the quantization is done. So let me show you in MATLAB how I've done these modifications to the decoder to put in this and work with integers. Okay. So the MATLAB code for the successive cancellation decoder. So maybe I should also keep this going. Okay. For the successive cancellation decoder for polar codes. So previously we didn't have the integer, the fixed point version of this code. So I've saved it as NR polar SE decode FP, and then I've put in the integer thing. So you can see what I've done. I've done the R max as 4. You could, I mean, you will have this code with you. You can try with 3, etc. if you think that works. Okay, and put max QR as 31. Okay, so this is the maximum integer received value. The other things don't change, nothing much changes, everything else is the same. You decode and all that, and now when you transmit, you will do the BPSK just like before. You will do the received value just like before. Okay, in the simulation, this is how it works. And then I will do the quantization. You can do the quantization in multiple ways. I have done it in a slightly different way here. You can see I have divided R by R max and then multiplied by max QR. Then I take the floor of it to get RQ. And then, so I am not clipping first. So I am doing the clipping a bit differently here. So you can see you can do R by R max into max QR and then you do the clipping. Okay, so this is the clipping comes here. Okay. So this is also fine. So you do R by R max into max QR and then you clip. And here you can see I've clipped up to max QR on the positive side. On the negative side, I've done minus max QR plus 1. Okay, so I'm doing minus 32 to plus 31, which is actual 2's complement representation of integers. Okay, so hopefully that's clear. So you'll see that this is equivalent. You can also do it the other way. You can clip R to first minus R max to R max, and then this will not be needed. You can just do the floor. Okay, that's also fine. So after this, nothing much changes. A couple of things to watch out for. So if you look at the F and G operations, so if you remember the polar decoder, we only do F and G. We don't do anything else in terms of operations on the received values. The F operation is okay because it doesn't do anything to increase the value of what's coming in. So it just takes minimum of the two values. So it doesn't need any special handling. On the other hand, G needs some saturation. The reason is, so what G does is adds two values. So if you take, for instance, plus 31 and plus 31 you add, you get plus 62. Okay, but you're allowed only to go between minus 31 to 31. You want to quantize it back. Okay, so that's why I've written the saturation. It saturates the FP value, and you can see the way I've written it. I've done max of x comma minus. Okay, so this will take care of the minus part. Then after that, I take a min of that max value comma max QR. Okay, so this will ensure that whatever value x is, it does the clipping. So the saturation does the clipping between minus 32 and plus 31. Okay, it won't allow the value to go above that. If it goes above that on either side, it will clip it to either plus 31 on the positive side or minus 32 on the negative side. So this is what I've done here. So the previously we did not have the sat x on the G function. So now we put the sat x also. Okay, so this few changes are enough to make sure your code will work with the integer side. Nothing more is needed here. Everything else is exactly the same, and you can work. Okay, so this is hopefully clear. So you have to make sure the received value becomes an integer. The saturation effect is something you have to watch out for. And if you're doing any operations in your decoder which increases the value, you have to saturate again. Okay, so sometimes when you saturate like this, you have to be paying some attention. For instance, in the LDPC code, there are two types of values. One is the LLR for the messages, the other is the LLR for the total LLR. Okay, these two are saturated at different levels. They have to be saturated at different levels, otherwise your decoder will fail. Okay, so I'll comment on that next. But this is something important. When you do operations, when you're expecting the value to grow, you have to saturate. Okay, so now let me move on to the LDPC code and show you once again how this was done on the LDPC code. Once again, you see here I have max R max is 4, and then I have max QR as 31. Okay, so this is the quantization for the received value. I also have a max Q for L. Okay, and this L values I'm saying is 127. I'm allowing it to go 2 bits higher in magnitude than R. Okay, so this is important because that L represents the total LLR, which can be larger, and then you have to subtract it from R to compute the extrinsic and all that. So you have to allow it to be large. Okay, so that's very important. And then other than that, what I do is largely the same. I'll compute the BPSK modulation, then find the received values. Okay, and then of course this is puncturing, and then after that I'm doing exactly the same thing. Okay, so I do the computation of the floor, right, convert it into an integer, and then you do the clipping. Okay, so this clips. Okay, so that's fine. I've done the clipping. Okay, so now in the decoder, so this is inside the LDPC decoder. You remember the LDPC decoder, you do row operations, right, in the layered decoding, row after row after row. You work with it, and then you subtract. You first subtract the total LLR minus what's already in the row, then you do the min sum on the row, and then you add that value back to L total. Okay. So, here is the subtraction happens here. The capital R is what is in the storage for the row processing. Okay. So, you do the subtraction and then you do some row alignment, and after that notice here I do this. Okay. So, anytime you do an operation like this, you have to also make sure that you quantize again. Okay. So, because this L has going from minus 127 to 127, this is only minus 31 to 31. So, this can go above 31. So, you quantize again, make sure it's quantized. So, this makes sure that your bit width, the number of bits you are allocating for the storage remains 5. Okay. So, that is very important, 5 or 6 in this case. Okay. And then you do the min sum operation here. The min sum does not require any checks for increase in value, because you are not doing any addition. So, that is okay. And then you have addition here again. Okay. So, notice what happens here. So, once you have the min sum value, you have to add. Okay. So, this is the addition part, and when I add, the temp ultimately becomes L. Okay. So, I have to quantize again, but the quantization is to max QL now. Okay. So, I am going from minus 128 to plus 127. Okay. So, I do that here to make sure I do not overflow here, and that is fine. Okay. So, these are the only changes. Other than that, there is nothing else to change, everything else works as such. Okay. So, converting your code to fixed point is a little bit easy to start with, but when you look at the operations inside, making sure that the bit widths are valid for the different types of numbers you have inside your decoder can be a little troubling. In the Polar code, it is very easy and simple. You only have to saturate the G operation. In the LDPC code, you have two different values. One is this R storage that you use for the row processing. The other is the L value, which is the total LLR, total belief. And as you keep processing, the L value has a larger quantization than the R value. So, you have to take care of that and keep saturating. Whenever you do addition or subtraction, you have to keep saturating and in a different way. Okay. So, that is something important. Once you do that, both of these will work. If you want, I can run these for you. Okay. So, let me show you how this decoder runs. I have set it up so that EB over N naught is 1.5 dB, maximum iterations is 10. Okay. And then I am running it for 100 blocks. Okay. Let us run this. Okay. So, it is finished running. It gave you some answers. Maybe you can't see that very clearly. So, maybe I should run it once again. I will run it once again just to show you how these numbers look. It's not too bad. We got 5 errors out of 100. Okay. So, it shows 55 errors out of 100. So, it shows that it works. It gave you some decoding. So, if you want, you can go to 2 dB. If you increase that, you will get to 0 hopefully. Yeah, so you had only 7 out of 100 in error when you went to 2 dB. Okay. So, that's the decoder. It works in a simple way. Okay. So, hopefully the fixed point part of it is clear. You can also run the Polar decoder. This is let us also run it at 1.5. Do not think, again 100 blocks. Okay. So, let us run this once again to be sure that we get something reasonable. Okay. It worked quite reasonably. You got 37 out of 100, and if you go to 2, you will get some performance. 12 out of 100 was an error. So this is how the fixed point is done. Okay.